Okay, so what I want to do today is just sort of go over the kind of just the intuitive picture of, we do an RF pulse, what does that look like to the M vector? And then we let it recover. What does that look like to the M vector? And then we'll talk about page 1 of the differential equations textbook. So how do you do a solution to the differential equation? And we'll just work through why that T2 solution, how we got that, because it doesn't look anything like the the initial differential equation. So you wonder, like, where did all the stuff in it come from? So that's the plan today. So let's just start off with. The last thing we did last time was we said this is what T2 decay looks like. It goes off, very rapidly. And then we separately said there's another graph. If you're starting here, this is what T1 decay, which is T1 regrowth, looks like. So this guy was T2 decay, and this was T1 decay, which is actually regrowth. So, but the problem is these are both happening at the same time. So T2 decay is basically the XY component decaying away, and then T1 decay is the Z component growing. So what does that look like under these two different conditions? So one, we just do what's called a flip. That's we turn on the RF, put some energy into the protons, and flip some of them so that they're the opposite direction from the magnetic field, and also line them up so that you get a coherent signal. And then separately, we turn off the RF and just allow the system to relax, as the physicist would say, meaning sort of go back to equilibrium. So what does that look like? So if we draw our coordinate system here, so here's this guy is supposed to be the x-axis coming out at you. There's the z-axis. And remember, I've rotated, for all these diagrams, I've rotated 90 degrees. In real life, when you're lying in the magnet, the z-axis is horizontal. So, and then this was the y-axis on this side. So what is the picture of doing a flip? Now, the thing I said about the flip, I babbled so many things, but generally you do a relatively short RF pulse. It might only be like, say, 500 microseconds. Like it might be like a half of a millisecond, or even less. And so during that time, there's not much chance, because the time scale on this, this is about like 100 milliseconds here. So if our flip only takes a quarter of a millisecond, our flip is going to be like right at the very beginning, so we can ignore. So if we do a very rapid RF pulse, we can ignore the decays because they haven't had time to occur yet. And so what that means is that in particular, the XY component won't change. And so what does it look like when in real life? So we start off with our M vector. So here's the M vector. And remember, the B vector is lined up with it, or the M vector is lined up with the B vector. So this is the direction of the strong magnetic field, and then here's the direction of the local magnetization in the little chunk of the brain. And so what happens when we turn on the RF? What happens is this vector just starts rotating down, and what does that look like? It kind of so here's where it starts. So it looks like this. So basically what it's, if you plotted where the vector is touching, this would be a sphere. That's supposed to be a sphere. So the vector doesn't change length, but it just rapidly changes direction. Now, I didn't draw anywhere near enough cycles here because it's doing 123 million cycles per second, so it's going very rapidly around there. And there's a lot more cycles before it actually starts to tilt down, because, so I've only sort of drawn it sort of like a cartoon here. But what happens is, basically, at some point in, later point in time, let me just make this guy a little bit more out in perspective, sort of coming out at you. Okay, it's coming out at you. So basically what will happen is the m vector will just rapidly precess around. So here's the m vector at some later point in time. It won't change length. And if you keep applying the RF, then what will happen is you will continue past the xy plane. You actually sort of go underneath the xy plane, sort of along a sphere. So that's what happens if we run Bloch equation solution. So if we solve the Bloch equation for that first part, I explained what the solution looked like, but I didn't write it out. On the Friday graduate session, I'll write the whole thing out so you can see how that solution actually works. But what it would do is it would just describe this pattern of the vector going across the surface of a sphere, sort of rapidly rotating around, and then not changing length, and then going eventually underneath the plane. So that's the result of running the Bloch equation solution for brief, for example, 100 microseconds RF pulse. So you just turn on the RF transmitter just for like a tiny bit of time, and all of this will happen in that 100 microseconds. It's a tenth of a millisecond. Okay, so that's the first part. And so where was that over here? So that was just like, that was like right here, right at the very beginning. So there was no decay. So that's why there was no decay. So now let's turn off the RF pulse, and then let the M magnetization recover. So that's the recover picture. And this is the time when it's going to be generating a radio wave, oscillating magnetic field that we can actually record and get the signal out. So the second one will be the signal. So this is run Bloch equation for relaxation. So relaxation means, returning to equilibrium. And we know what the equilibrium is. If you go in there for a long time, you're just lined up like we started. So this is the equilibrium. So that means like where we're starting. Equilibrium start. Okay, so now we want to just relax. And so what is relaxation? What does physicist relaxation look like? So that looks quite different, because now we've got to run these two things at the same time. So here's the x component sticking out at you. Here's the z component, and then here's the y component. So that's, and let's say we just start here, where so here's our starting. Okay. So that's our start. So remember, it's going around really fast. And it will continue to go around really fast if we run that first term, the solution to the first term of the Bloch equation. And so what does this look like? Well, it's sort of, it continues around, but then very rapidly it gets much shorter. And I've exaggerated how much it's gone up in the z direction. So what's going on there? Well, this is the T2 decay, which is the reduction in the xy component, the component parallel to the plane. So as that component of the m vector gets very short, the m vector gets very close to the z-axis. But it's still precessing, and then during that whole time, this T1 regrowth is occurring, and so what happens then? Well, it just sort of goes. I've exaggerated how far away it is from the axis, but it sort of precesses around until we finally get up to where we started. So that would take like about 2 seconds. And so when we're done, we're back to where we started. So that's the m after 2-3 seconds. So that's kind of the basic, that's the picture you should have in mind. So what happens is you do an RF pulse, it's just like hammering on the thing. And when you hammer on it that way, then you don't change the length of the vector. The vector stays the same because the decay hasn't had time to occur. And then it just, if you run that solution to the first term of the Bloch equation, it just cycles around the sphere very rapidly. And then you turn it off, and then the decay starts. And so what happens to the decay? Well, first you lose all the xy component very quickly because T2 decay happens, in a 20th of a second. And then it takes a couple seconds until you sort of regrow. So basically there'll be no signal. I drew this too big here. After about 100 milliseconds, there's going to be basically no signal at all coming out. No recordable signal. And so the vector will just slowly, grow back up until it gets back up to the mz0. Okay, so that was run Bloch equation for relaxation. Okay, so any questions about this? It seems reasonably clear. So I mean, we're just going to basically just describe the equations for this, but geometrically this is what's going on. So rapid T2 decay, slow T1 regrowth. They're both occurring at the same time, but conceptually we separate them out and sort of deal with them one at a time. And the reason we can do that is because they're perpendicular to each other. Okay, all good, no questions. Okay, and that's it. Sort of seems when you see this, you go like, wow, this is it's not much to it. The equations sort of get more and more complicated, but it's actually reasonably simple. How could how could that be the whole explanation? But pretty much it is. Okay, I'll leave those up here for a second in case anybody has. The top one? No. The top one was RF excitation. So T1 and T2 decay were occurring during this, but it's such a short time. So this is short RF excitation. So T1, T2 decay can be ignored. Yeah, no, that was, so T1 and T2 decay were occurring, but it was such a short time that we did the excitation, there was no time for them to actually sort of do anything. It was right at the very beginning of the graph. Yeah, so that was short RF excitation, and now this guy is T2 and T1 decay. No RF input. This will be generating, RF means radio frequency. So there's no input. No input, we're just record RF. So that makes a recordable signal come out. Yeah, so in some sense, T1 and T2 decay were happening in both, but this was such a short time. This picture was just, it was only less than 1 millisecond, so it's such a short time that you can ignore it. And here now, so this picture, this picture is like 1/10 of a millisecond, and this picture is like 3 seconds. Okay, so yeah, different time scale for those two pictures. Okay, so now we have to do page 1 of the differential equations textbook, but hopefully in an understandable way. So last time what we said was we had the differential equation, which differential equation just means like an equation with derivatives in it. So we had a differential equation, and that differential equation was the change in the xy vector over a short period of time. And this is just the T2 decay part of the Bloch equation, equals this relatively simple equation, which is just the current value of the, I'll put a T in there. So whatever the current value of the XY magnetization is, divided by T2. So that's a very simple equation. So all it says is the amount of change is proportional to how much you currently have divided by something. That's in words. So so depending on how big T2 is, that will affect how big this guy is. So if T2 is really big, it's in the denominator, and so that means there's a small change. So large number in the denominator, long time constant, means a small change for the next time point, which means that it doesn't decay as quickly. So even though there's only like 3 parts of that, just make sure you understand all the parts. So that was the differential equation. And then we said we solved that. And the solution was the following. So this is solution. So the solution was the mxy value at a time t. So once we have the solution, we can sort of calculate for any old time what the magnetization is. This one just says like an instant into the future. So the solution was equal to this mess. It was the x. Remember this whole thing, which was the whatever the XY magnetization was just after the RF pulse. That was this guy. So this is mag XY just after RF. Could be anything. You might have turned it on, the RF on for a long time, short time. And then, times e to the minus t over t2. So that's the solution to the equation. And so the plan for today is, why is that a solution to this equation? What does it mean to be a solution to the equation? And so so normally when we think of doing a solution to an equation, you might have an equation like 5 equals x plus 2. And so when you have this equation, you can sort of solve for x. And that's kind of what we're doing. We're doing something like that. So this is just like a simple, this is just a simple variable. Okay, so the variable is just a number. So what we're trying to do with when we solve a differential equation is something similar, except that we're doing it with an equation. So the answer is an equation. So basically what we want to do is find equation, not a number. So find the equation, whose derivative is the differential equation. So that's what we're trying to do. So basically what we're trying to do is we're just trying to find some equation that when you take the derivative of it, you get this. So the idea is that this equation right here, if we take the derivative of it, we should get the differential equation. And so what we're doing is we're solving, we're solving for this guy. So this guy is, so here's the important point. This guy is the unknown. Like x. Like x down here. So we have an unknown equation instead of an unknown number. So that's the basic plan. And then along the way, what we want to do is, where did mxy at the starting point come from? Because that wasn't in the original differential equation. So it turns out that this thing's called an initial condition, and so we'll try to understand where that comes from. Why do you get some additional thing when we solve this equation? So the first plan is So the first plan is, where does e to the x come from? Because when you first look at differential equations, you go like, why, how does that relate to that? It just sort of seems like it just came out of nowhere. Okay, so everybody got the picture. It's just like solving a regular equation, except that instead of the answer being a number, the answer is an equation. Okay, so let's try to make this as clear as possible. So first of all, why do we often end up with e? And so if we look at, so if you go into MATLAB and just plot e to the x, just go in and plot e to the x, not minus x, just e to the x, and just look at what it looks like. How would you plot that in MATLAB? It'd be like x of something like that. Just plot that. And what you see, it's actually kind of a cool special function. It sort of looks like this. Just goes up. So this is, e to the x, not minus x, and this is x. So e to the x has this, it's kind of a special function, because if we go someplace on e to the x, at some x value, and look at the slope, which is the derivative. So this is the derivative of e to the x, which we can write like with just an apostrophe like that. So if we just take the derivative of e to the x, it turns out it's equal to the slope. So the value of e to the x is equal to the slope at that point, which is the derivative. So it means that, the derivative of e to the x, so here's e to the x, we take the derivative, just equals e to the x. And when we look at this equation, it's only got 3 parts in it, but say we just threw out the T2, or made T2 1, then we'd only have 2 parts in it. And so if we threw out the T2, what does that equation say? It just says the derivative of a function equals the function. That's like this. So that's why whenever you have a differential equation where you've got a derivative on one side, and you have a derivative of a function on one side, and you have the function on the other side, well, this is going to be a natural thing that you want to put in there because the derivative of this thing equals the thing. And that's exactly what this equation says. Like the amount of change, the derivative in the mx just equals how much mx you got currently. And so there's a whole bunch of things in the world that are like that depend on how much you have left. And this is an example of one of them. So like, how much is going to happen in the future depends on how much stuff you have left at a given point in time. Okay, so let's just do what we said down here, which is start off with our function with an unknown in it, present a solution, take the derivative of the solution, see if we get back to the original one. So I'll try to do it maybe a little clearer than we have in the notes. So we start off with the differential equation, and this time we're just going to write it a little more facelessly. So here's the differential equation, and we'll just write it out with an apostrophe to get rid of some of the junk so we can sort of concentrate on the main points. And so basically the derivative of this function of some unknown function at a particular point in time is just equal to minus 1 over t2, just take this constant out, times the function. So that's just, all I do is just rewrite the equation sort of even simpler. So, derivative of function equals a constant times the function at that point in time. So then we said the solution is, here's the function at a point in time, so we're going to just define what that function is, not the derivative of it, is equal to e to the minus t over t2. Or you could just write it out as, e to the minus 1 over t2 times t. Same thing. So that was our solution. So here's the solution. Okay, so now we want to take the derivative of that guy just to see if we've done the right thing. And so what would that be? That would be, so now take the derivative of this guy. So here's the derivative, and so now we've got to take a derivative. So how do you take a derivative? Well, the rules of the derivative are that we have to use what's called the chain rule. We have to take the derivative of the exponent and then multiply it by the whole thing. So like, just take a simpler example, like what's the derivative of 2x? So the derivative of 2x is just 2. So we just end up with the constant in front. And we lower the power of x, because that's x to the 1. So when we take the derivative, we lower the power of that guy to 0. And then that x turns into a 1, and then we multiply by the constant. So that's the simple derivative that we're doing here with this thing. And so the answer is we take a derivative of the exponent, and that's just going to be minus 1 over t2, because the t will have gone from the power 1 to the power 0, and it will turn into a 1, and so we just end up with minus 1 over t2. So that's basically, that's the derivative of this guy. And then we multiply by the whole thing. So times, e to the minus t over t2. So now did we so this is test, take derivative. So the question is, did this work? And so how do we determine whether it's worked or not? So the problem here in understanding differential equations is all the substitutions. So I tried to make it as clear as possible. So what we want is, the question is, did we get back to this thing? So the question is, did this guy, get back to that guy? So did we get back to that guy? And so how can we tell that we got back to that guy? Well, this guy right here is equal to that one. And that's our unknown. So this guy is the unknown. That's an important point. It's not defined here. So our unknown is the function, and here's our proposed solution. And so now, when we take the derivative of it, we get this. And so then the question is, does this equals that? Does this one equal that? It does, because basically that's obviously the same. And then this thing is our unknown function. So it's the problem in understanding this, like I said, it's the substitutions. So this thing stands for an unknown function. Here's our proposal for what that unknown function is. Now we want to test, so we take the derivative of this guy and we get this. And what this says is it's minus 1 over t2 times our unknown. And so we got that back. So this one is the same as that one. Different symbol because we've replaced the m at time t with an actual function at time t. Okay, so this is page 1 of the differential equations textbook. If you can understand this, then basically there's just more of the same under more complicated conditions in the rest of the book. But the problem is sort of understanding the idea of an unknown function. What does that mean? Okay, so let's take another one a little bit quicker. So here's another one. So let me just write out, let's put a boundary here. So we write out the differential equation again. So here's the differential equation again. So the derivative of this equals minus 1 over t2 times some unknown function. So let's try another solution. So this other solution is some constant. So not the derivative, our solution function equals some constant, any old constant, times e to the minus t over t2. So what does that look like compared to here? It's the same thing as this one, but it's got like 4 in front of it or 2 in front of it, something like that. So it would be like mt. So this is like mt equals 1 times e to the minus t over t2. This is, mt, for example, 2. For example, 2. This is 2 times e to the minus t2. So does this one work? Turns out this one works too. So how do we do that? We take the derivative again. So if we take the derivative, here's, first we have to take the derivative of the constant, so of the exponent, sorry, and that's 1 over minus t2. And then we multiply that by the whole thing, and the whole thing is whatever the constant was, times e minus t over t2. And so the question is, does this one work? Well, it actually is kind of the same thing. So if you look at this one now we've got this thing here. This whole thing is our unknown, and that's the thing we're proposing, as our unknown, the answer to this unknown. MT is unknown. So then the question is, if we take this guy down here, is this guy actually, equal to this one? Question mark? And the answer is yes, because it's minus 1 over T2 times the unknown function, which is this guy. So magically, that's our solution as well. And so in fact, there's an infinite number of solutions. Any old thing multiplied by e to the minus t over t2 works. So that's another thing that's kind of like, so here we just had one solution, but now we've got like an infinite number of solutions. That's kind of disturbing. But let's just draw them out to sort of see what they look like. So now I've got a nice amount of space here. So let's draw out some of these solutions. So let's start with, say, start at 1 here for our first one. So if our first one, what does it look like? Well, it's just, if you plot out this first solution, it will look something, just look something like that. Okay, so that would be this guy. Okay, so that's what the solution looks like. So now let's just plot out this solution, which is another solution. It's a perfectly good solution. So that one will start at 2. Say we just plot it out for 2. And so what's going to happen is this one is the equation is just going to be 2 times this same equation. So basically you could just sort of, it's going to be here, and it's going to be, here, it's going to be here, and it's going to start there. So basically this would look like that. So that's another solution. So that guy, this guy is our solution here. I didn't label this. Should label these. This is differential equation again. That wasn't changed. This is solution number 2. This guy was solution number 1. And test, take derivative. So now we've got this second solution. So here's this second solution down here. So this guy looks like that. So the amazing thing is we've got a whole infinite number of different solutions. Each one of these is a perfectly good solution to the differential equation. And so how does that work? Well, what this equation says is, the amount of change in a small amount of time is proportional to how much you have left. And so if you're starting, here, you'll go down a little bit, and then that will be the derivative. It will say, like, what is the slope of that guy? So this is where we're going to be in the next time point. But if we just go and start on this guy, what's going to happen? Well, the same equation will drop it more because we're starting at a higher point. There's more stuff that we've got here. So the exact same equation for the solution is going to work in all these different conditions. It just depends on how much you got left. And if you started from, minus 2, or say like minus 0.5, like what if we started, minus 0.5, it would actually go up instead. So basically there's just a whole bunch of infinite number of solutions here like this. And there's all different ones. And all of those are contained in this one simple differential equation. So that pretty much explains where this extra thing came from. So what is this extra thing? This extra thing is basically what we call the initial condition. So the initial condition, it's not in the differential equation. because the differential equation just says for a tiny bit of time in the future, the change is proportional to how much you got left. But it doesn't tell you where you started. And so this extra number, sort of like, this thing is just a number, remember? This guy's just a number. That whole thing is just one number, and that's the initial condition. And the initial condition is how much you start with. And that tells you which of these infinite number of differential equation solutions we're going to use. So if the initial condition is 1, then we use this guy. If it's 2, if it's, in between 1.5, there'll be 1 in between. So our initial condition is this number, how much XY magnetization you started with, right after you turned off the RF pulse. So that's just a number. It's not in the differential equation. It came from the solution. So it's kind of a weird solution to the equation that has sort of an infinite number of answers. But it helps us because now we know we can just draw our graph. We can say, okay, say we had this much, mxy at the point right after we turned off the RF pulse. This is what's going to happen by just plotting this this equation right here. And so if you look at this equation, it's pretty much this one, this solution number 2, the value of the XY magnetization at time t is some constant times this e to the minus t over t2. That constant is the mxy 0 plus. So this guy out here, these guys are that constant, is that guy. And so that constant, that doesn't change when you run this equation. That constant is just whatever you started off with. And so this solution to the differential equation, adapts to all these different starting conditions or initial conditions. This is an initial condition. So that's time here. And this is just the value of the XY magnetization at time t, going that direction. Okay, finished a couple minutes before the bell. So let's so I have some questions. So like I said, this is, if you can, it's on page 1 of the differential equations text, but if you can understand this, then you basically can understand like what a differential equation is. So it's just an equation that has, instead of an unknown number, it's got an unknown function in it. And so mxy at point time t is some unknown function. We don't, it's we don't know what it is. And so here's a proposal for what it is. And then how do we test that? We take the derivative of this guy and see if we end back up with that. And the main problem is just sort of understanding like the substitutions, like what, so this is an unknown. Here's a proposal for it. How do we test it? Take the derivative, then you have to remember how to take derivatives, but it's not too hard. And then you test, does this thing equal that? And it does, because it's minus 1 over t2 times the solution function. Okay. Yes?
How would you guess which proposal equation you were?
Well, yes. Now that's what the whole rest of the textbook is about. So, yeah. So you can see there's a clear problem here. Like, how do you actually, So there's a whole sort of like algebra of differential equation solutions where you propose different things, or you've seen some other differential equation and it was solved by doing this, and this one kind of looks similar. Let's see if this one works. Yeah. So you can see what the problem is. It's hard enough to understand this one, but if you can get through this one's an easy one. And so yes, exactly, you hit the nail on the head. That's exactly what the problem is. How do you solve the differential equation? You just sort of cast about for different functions that when you take the derivative of them, it works back to your equation. And so that's exactly what the problem is. And so people have worked out all different tricky methods for doing this. And it would take, like a whole year to just enumerate the ones that they have. But this one's a relatively easy one. We'll just do, next time I'll do one more that just has one more part, one additional thing in it, so you can see how what some of the tricks are. But yes, that's a very good question. How do you figure out the solution? So in this case, there's a lot of simple differential equations that are like this, where the amount of change is proportional to how much you have left, and those will always be solvable by this, using this e to the x equation, because it has that interesting property that the derivative of it is equal to the value of it. And that's exactly what we're looking for here. The derivative of something equals the value of it. The only additional thing was we have that constant in there. Yeah.
What is the initial condition connect back to, just like when you graph it in MATLAB? How can you graph it?
How would that fit back, like if you wanted to graph it in MATLAB? So you would just take this equation, and this whole thing is just one number. It's a constant. So you just put in, if you were going to put it into MATLAB, you would just say, m, basically equals, 2 times, exponent of, x, something like that. But, instead of x, you might want to put in sort of, x, divided by t2 with a minus in front of it, like that. So you would just stick it in as a number. Or you could put it in as, as a vector and plot out a whole bunch of different solutions if you wanted to. So you'd have to sort of make this into a vector by running this equation multiple times, get a bunch of time points on that, and then plot those time points. So typically you would say, like, make a vector out of, running this equation for a whole bunch of different values of x or t. Yeah, so I'll put minus t there, make it a little clearer. Yeah. Oh, into MATLAB? Yeah, so how would you get it in? Well, you could get it in various ways. So like if you just take, like the scanner will just spew out a whole, matrix of numbers. And you could just literally just take that matrix of numbers, if you didn't want to do any corrections on it, and just, say, do a Fourier transform on it. And you could just literally take that matrix of numbers off the scanner and just do FFT on it. So, but the first thing to do is just plot e to the x, Just figure out how to plot e to the x, how to get a vector of numbers, and then plot a vector of numbers. And once you've done that, then you could say plot 2 times e to the x, and then plot, e to the minus x, and then plot, e to the minus x divided by 2, and just see what the graph does. That's the way I do math. I just operate the MATLAB and just see where stuff goes, and then you get a better sort of more motor system feel for how the equations work. Yeah. What is the m vector? And that's a good question. Yeah. So what is the m vector versus the b vector? So basically what it is here you are in a magnet, and so you're sitting in this giant B field here like this. So there's the B field. And what the M vector is you just go to a little chunk of your brain. So that B field was caused by the superconducting coils. So go to a little voxel in your brain, and just in that little voxel, just figure out which way the local magnetic field, which is the result of all the proton magnets pointing in different directions, some lined up, some not lined up, you just add them all up, and then you end up with some, M vector. Now it's a tiny, teeny, tiny vector compared to this gigantic big one. So in real life, it's like here's the B vector, and then here's this little part, it's a teeny, tiny little, M vector. And what is that M vector? It's just all the proton magnets. They're all in slightly different directions at any instant in time. You just add them all up tip to tail, and you get a little vector. And so that's what the M vector is. So this one is sort of being applied to the entire brain, but the brain has its own mind. It's got a bunch of its own magnets in it, and they're all pointing in various directions. And so this is the magnetic field coming from the big magnet, and then this is the magnetic field coming from, this guy is the magnetic field coming from the sum of all the local magnets that are in there. So that's a conceptually different thing. And you could just sort of think of it, it's not any different than, you've got the MRI magnet turned on, and then you just get a little refrigerator magnet and bring it. It has to be a pretty small one, otherwise it's going to be ripped out of your hand. So bring a little teeny tiny refrigerator magnet in there and stick it in there, and there would be some force on it. If you moved it around, you would get different forces, and that's what the M vector is. So it's just the local sum of all the little magnets of all the protons, all summed up. And it's going to be different. Each little voxel is going to have potentially a different M vector. It doesn't have to be the same. It can be quite different in different voxels. Yeah, so that's an important point. It's like going to be different for every single spot in the brain. And if you just go in there, don't turn on the transmit coil and just sit there for 5 seconds, then they'll all be lined up. All of them will be all lined up throughout your entire head, all the M vectors. And if you turn on the RF, then they'll start to sort of precess around, and then their length will change, they'll decay away, and then they'll slowly grow again. So that whole picture that I had drawn down here, it's all sort of rotated 90 degrees. It's happening this way. So you go on the magnet, all the little vectors grow up after like about 5 seconds, and you turn on the RF, and that makes it go around the sphere like that. And then you turn the RF off, and then it quickly shrinks down to almost nothing, and then slowly expands again in that direction. The M vector. And that's just all the sum total of all the little magnets all summed up for each little chunk. Yeah, so it's important. They're both magnetic field directions, but they're coming from different things. Okay, differential equations, page 1. Yeah, it took me until I was like about 60 until I finally, went through page 1. But these books are good. They don't need any battery. Battery's dead. They still work. So there's certain advantages. Okay, any more questions? Good so far. Okay, so next time we'll come back. We'll do the T1 decay. It's a little more complicated. I have one more number in it, and sort of figure out how that one works. And then on Friday. That is Friday. And then I'll also go over some use of matrices for rotating things, because that's one thing that we're going to have to sort of get a handle on. How can you represent a rotation of a vector in a matrix? So that's the other topic. And that's useful for a lot of other things. It's useful for aligning brains, for instance. So if you want to align a brain, that's actually sort of rotating the brain, or maybe scaling the brain. So we'll go through the simple math of that. Okay.